Okay, welcome back to this second class on number properties. So we are still discussing arithmetics and we are talking about number properties. So in the last class we went through integers, even and odd numbers, factors and multiples, HCF and LCM. And today we want to move on to the next subtopic under number properties, which is prime numbers. Now, what are prime numbers? Prime numbers are integers greater than 1 that have only two positive factors, that is 1 and themselves. So we are talking about all positive numbers that have only two factors. That is, those factors are 1 and the number themselves. So these numbers are called prime numbers. And all prime numbers are greater than 1. Note that all prime numbers are greater than 1. So, and that means 1 is not a prime number. So examples of prime numbers are 2, we have 3, we have 5, we have 7, we have 11, we have 13, we have 17, 19, 23, 29, 31, and so on. So all these numbers, they are divisible by only 1 and themselves. So they are called prime numbers. Now note, only 2 is even among the prime numbers. The rest are odds. Alright? So among all the prime numbers, only 2 is even. Others are odd numbers. So that is why we call 2 an even prime. It's an even number and it's also a prime number. Okay, now moving on, we have what we call prime factors. Now what are prime factors? Prime factors are factors of a particular number that are prime numbers. Alright, that are prime numbers. For instance, the positive factors of 12 are 1, 2, 3, 4, 6, and 12. So these are factors of 12 actually. But when you look at all these factors, you see that some of them are prime numbers, and those are 2 and 3. So because 2 and 3 are factors of 12 and they are prime numbers, they are therefore called prime factors of 12. Prime factors of 12 because they are factors of 12 and they are prime numbers. So we call them prime factors of 12. Now, we have what we call prime factorization. Now, prime factorization is simply the process of expressing an integer as the product of its prime factors. Okay, so when we write our number as the product of only the prime factors, then we have what we call prime factorization of that number. For instance, 100 is 2 times 5 times 2 times 5, which is the same as 2 raised to the power 2 times 5 raised to the power 2. Alright, so you can follow these steps to do this. For instance, using the same 100. That is, if we want to express 100 in prime factorization, you can just go by breaking the number down to its its factors. For instance, 100 is 10 times 10, and 10 can be written as 2 times 5, and then times another 10, which is 2 times 5. So, and this gives us 2 raised to power 2 times 5 raised to power 2. So here we've been able to express 100 as the product of the prime factors. You can see that all these numbers 2 and 5, they are factors of 100 and they are prime numbers. So they are prime factors of 100. Another way you can do it is to use a long division method. 100, then you begin to divide by using only the prime numbers that you know can divide this number 100. So 2 can go. So 2 in 100, I have 50. 2 again in 50, that will give me 25. Now 5, then I have 5. Then 5 again, I have 1. So this means my 100 will be 2 times 2 times 5 times 5. And that is 2 raised to the power 2 times 5 raised to the power 2. So This is how we express our numbers in prime factorization. Let us look at another example. Let's say we are looking at, let's pick 60 for instance, and I want to express it in prime factorization. This is simply 20 times 3, or you could say 30 times 2. Anyhow, we still have the same thing. Then I can have 20 as 4 times 5 times 3. Okay, now my 4 in prime factors can be written as 2 raised to the power 2. 5 is already in prime number, in prime number. 3 also a prime number. So it means my 60 is 2 raised to the power 2 times 5 raised to the power 1 times 3 raised to the power 1. So this simply shows to me that the prime factors of 60 are 2, 5, and 3. Alright, so that is how we can simply express our numbers in prime factors. Let's take a one large number. Let's say you are looking at 200,000. 200,000. How do we express it in prime factorization? Now, my 200,000, don't forget, is same thing as 2 times 100,000. Okay, and my 100,000 can be written as 10 raised to the power 5. And I can also write this as 2 times my 10 is same thing as 2 times 5, then power 5. Okay, so now this means I have 2 times, when I remove the brackets, I'm going to have 2 raised to the power 5 times 5 raised to the power 5. Now at the end, this one has power 1, so that means I'm going to have 1 plus 5, giving me 2 raised to the power 6 times 5 raised to the power 5. So here it shows that the prime factors of 200,000 are just 2 and 5, but the powers are 6 and 5. So I have 2 raised to the power 6 times 5 raised to the power 5 to give me 200,000. That is how to express numbers in prime factorization. Okay, so that is how we express numbers in prime factorization. Now, what can we use prime factorization for? The uses of prime factorization. Now, we have so many applications of this in order to simplify our work. So, number 1, we use prime factorization to determine the number of positive factors of an integer. Alright, to determine the number of positive factors of an integer. That is, if I want to know the number of positive factors an integer has, maybe I want to know how many factors 144 has, or maybe I want to know how many factors 1,000,000 has. Now, it may be difficult for me to list the factors before counting them, because there is no time to do that in the exam situation. So we use prime factorization to do it in a faster and easier way. Now, the number of positive factors of an integer a raised to the power x, b raised to the power y, c raised to the power z, where a, b, and c are prime numbers, is giving us x plus 1 bracket y plus 1 bracket z plus 1. So now, what are the steps? First, express the integer in prime factorization. That's the first thing you do. Then after that, add 1 to each power of the prime factors. Then C, multiply the results. Simple. Just express the prime factorization, add 1 to each power of the prime factors, and then multiply the result. Then you have the number of positive factors of that integer. Now, for example, first example here, example A says, how many positive factors does each of the following integers have? How many positive factors does each of the following integers have? So A, 144. So we want to know how many factors does 144 have? Now, let's follow these 3 steps and see the number of factors 144 has. So first thing we want to do is to express our 144 in prime factorization. So 144 is equal to 12 times 12, and 12 is 3 times 4, and 12 is another 3 times 4. Now we express 4 in prime number since it's not a prime number. Now we have 3 times 2 raised to power 2 times 3 times 2 raised to power 2. So at the end we have 2 raised to power 2, then plus another power 2, making 2 raised to power 4, times 3 raised to power 1, so 1 plus 1 will give us 3 raised to power 2. So here we have our 144 in prime factorization. That is the first step. The second step is take the power on each prime factor, add 1 to them. So we have first, which is 4, add 1 to it. Then we have the second one, which is 2, add 1 to it. So the third step, multiply the result. And what is the result? We have 5 then times 3, which gives us 15. So this means 144 has 15 positive factors. 15 positive factors. Alright, so that is how we can use prime factorization to solve or find the number of positive factors of an integer. Okay, so we could pick another simple number. Alright, let's say a number we are familiar with, maybe 30, and let's see how many factors 30 has. Now first, express in prime factorization. So we can do 6 times 5. 6 is 2 times 3 times 5. So all the numbers are already prime numbers. So that's the prime factorization of 30. Then step 2, take the power on each prime factor, which is 1 for 2, add 1 to it. The other one is also 1, add 1 to it. The other one is also 1, add 1 to it. Then you have 2, this one also 2, this one also 2. So we multiply them, and that gives us 8. So meaning 30 has 8 positive factors. Let's list the factors and see. 1, 2, 3, 5, 6, 10, 15, and 30. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 factors for 30. So that's how I use our prime factorization to find the factors, positive factors of any integer. That's the number of the factors, actually the number of the factors of that integers. Let's look at the second example, example B. So example B says we should find the number of factors of 500,000. That is, how many positive factors does 500,000 have? So let's see how many factors 500,000 has. Now let's take the first step by expressing our 500,000 in prime factorization. So we have 500,000 in prime factorization. First, this is something as 5 times 100,000, just like we did for 200,000 the other time. So this is 5 times 10 raised to power 5. So this is 5 times, so you can write out 10 as 2 times 5 all raised to power 5. So this means we have 5 times, so when we remove the brackets, we have 2 raised to power 5 times 5 raised to power 5. Now this is something as 5 raised to power 1. So we have to have 2 raised to power 5 times, so 1 plus 5, we have 5 raised to the power 6. So this is our 500,000 in prime factorization. Now the second step says take the powers on each factor and add 1 to them. So we have 5 plus 1 and then 6 plus 1. Now 5 plus 1 will give us 6. 6 plus 1 will give us 7. So the third step says multiply the result, and when we multiply we have 42. So this means 500,000 has 42 positive factors. 42 positive factors. All right. Okay, so that is how we can use prime factorization to find the number of positive factors of any integer. All right, let's look at another way we apply prime factorization. So 2, we use it to determine the factors of an integer. So if we need to know the factors of a particular integer, we can also get to know that using the prime factorization. That is, if this one is a factor and that is not a factor, and so on like that. So let's look at this example 1. It says if n is equal to 14,400, which of the following is not a divisor of n? That is, in this case, they are using the word divisor for a factor. So just note that. So here they want you to find the factor. Which of the following is not a factor of 14,400? All right. So let's see how we use prime factorization to solve this problem. Okay. So the question is asking us that which of these options from A to E is not a divisor, that is, it is not a factor of n, that is not a factor of 40,400. Well, you can always jump to your calculator to to know what the result will be by dividing 40,400 by 8 and see if it gives you an integer or not. Anyone that does not give you an integer, that means that is one that is not a divisor. That would be the right answer. But anyone that gives you an integer means it's a divisor or it's a factor. Okay, but if I don't want to use my calculator, then I can use my prime factorization method. And what do? I'll first express my 14,400 in prime factorization. Okay, now to do that, 14,400 is the same as 144 times 100. 144 times 100. And this 144 is 12 times 12, while 100 is 10 times 10. So now my 12 is 3 times 4 times 3 times 4. Now the 10, 2 times 5 times 2 times another 5. So at the end, if you look at this, I'm going to have my 2 twice, that's 2 raised to the power 2, times I can have 3 raised to the power 2, times 4 is another 2 raised to the power 2, times another 4, which is another 2 raised to the power 2, times 5, which is 5 raised to the power 2. Now my 2, I have 2 plus 2, that's 2 plus 2 plus 2, so I have 2 raised to the power 6 times 3 raised to the power 2 times 5 raised to the power 2. Alright, so this is a prime factorization of 14,400. Now, how do I use it to get the factors? It simply means that, now this makes it clear to me that, okay, any of these numbers that is not found here cannot be a factor, because a factor must be found in its multiple. So if I say a number is a factor of an integer, that means I can get that number in that integer. If I cannot get it in that integer, then it is not a factor. Okay, so for instance, now let's check the options. Option A says 8. Of course, 8 in prime factorization is 2 raised to the power 3, and you can get 2 raised to the power 3 in our 2 raised to the power 6. So meaning 8 must be able to divide 14,400 with no remainder, so 8 will be a factor. So it cannot be our answer. If we look at B, we have 27, and 27 is 3 raised to power 3. But as you can see, I have 3 raised to power 2 in my prime factorization. So there is no way I can get 3 raised to power 3 in 3 raised to power 2, and there is no any other 3 from the factorization I have here. So it means that this 3 raised to power 3 cannot be a factor of 14,400. If I use 27 to divide 14,400, it will produce a remainder that is not 0. So that means 27 will not be a factor of 40,400. So definitely that is our right answer. So 27 is not a divisor, it's not a factor. We can check the rest. 32, that is 2 raised to power 5. We can find 2 raised to power 5 in 2 raised to power 6. So it's a factor. If we check D, which says 75, my 75 can be written as 25 times 3. You may not even express it in privatization. So 25 is 5 raised to power 2, which is here, and I can get 3 from here. So definitely it's a factor. If I look at E, which is 90, my 90 is 9 times 10, or 9 is 3 raised to power 2, 10 is 2 times 5. So 3 raised to power 2, yes, is available. 2 I can get from here, 1, 2. 5 I can also get from here. So meaning that E will also be a factor. So the only one that will not be a factor is 27, because it has 3 raised to power 3, and the maximum we have in this factorization of 40,400 is 3 raised to power 2, so it cannot divide it. So that is how we can use prime factorization to know the factors of a particular integer. Okay, so now example 2. The question says, how many common factors do 800,000 and 1 million have? How many common factors do 800,000 and 1 million have? I can tell you this question is a real GRE exam question, past question. All right, now how can we find this? Remember, we already talked about common factors. Now this means you have to remember our common factors. So we're looking at the number of common factors of 800,000 and 1 million. Now before we go to the solution of this question, I want you to recollect something that we discussed in the last class, which is this note B that says the common factors of 2 or more integers are the same as the factors of their HCF. Remember? Yeah, the common factors of 2 or more integers are the same as the factors of their HCF. So this rule is simply what we need to solve this particular question here. Okay, so that means if we want to find the common number of common factors, and we know that the number of their common factors must be the same as the factors of their HCF according to that rule, then simply all we need to do is to first find the HCF of 800,000 and 1 million. Remember that HCF means the highest number that will divide these two numbers with remainder 0. The biggest that will divide 800,000 and also divide 1 million. So of course you can easily think about that kind of number. I think it shouldn't really be a problem. You can think from 100,000 and see if there's a higher one, and so on like that. So okay, let's see how we answer this problem. Now we have 800,000 and also 1 million. So we want to know the number of common factors the two of them have. Now first, like I said, according to the rule, the number of their common factors will be the same as the number of the factors of their HCF. So that means we need to first find the HCF of 800,000 and 1 million. So now remember, we can use prime factorization to find the HCF of our number. So for 800,000, using prime factorization, okay, we have 8 times 100,000, and this is 8 times 10 raised to the power 5. 8 is 2 raised to the power 3, 10 is 2 times 5 raised to the power 5, and this will be 2 raised to the power 3 times 2 raised to the power 5 times 5 raised to the power 5. Now that gives us 2 raised to the power 8 times 5 raised to the power 5. So that is our prime factorization of 800,000. Now what about 1 million? The prime factorization for 1 million. Okay, so 1 million is 10 raised to the power 6. 1, 2, 3, 4, 5, 6, 6 zeros. So which means 2 times 5 raised to the power 6, and that will be 2 raised to the power 6 times 5 raised to the power 6. Simple. So that's the prime factorization for 1 million. Now to find the HCF, remember that you look for the common factors for the two numbers, and of course the common factors are still the same, 2 and 5, and then we pick the one with the lowest power. Recall, lowest power. So we have 2 raised to the power 8 and 2 raised to the power 6, so that has to be 2 raised to the power 6, then times for the 5 raised to the power 5, 5 raised to the power 6, we pick 5 raised to the power 5. So definitely this is the HCF of 800,000 and 1 million in its prime factorization. In its prime factorization, that's the HCF. So now, since we know that the number of factors of this HCF must be equal to the number of common factors of 800,000 and 1 million, so then our problem is solved. All we need to do is to find the number of factors of HCF. And recall from our number 1 application of prime factorization, to find the number of factors of an integer, what do? Express in prime factorization, which we have already, then take the power 6, add 1, then 5, add 1. And when we do that, what do we do next? We multiply the result. That is 6 or 7 times 6. Okay, so this means we have 42. So this means the number of factors of our HCF is 42, and that definitely must be the number of common factors of 800,000 and 1 million. So our final answer for this question will be 42. Okay, so that is how we can find the common factors, the number of common factors of 2 or more integers. Just get their HCF, and once you get the HCF, express in prime factorization, then use the first application, that is add 1 to the powers, multiply. So the number of factors of the HCF will be equal to the number of common factors of the 2 or more numbers you have. Alright, so that is how we can find the common factor. So that means 800,000 and 1 million have 42 common factors. 42 common factors, which are the same as the factors of their HCF. Okay, so now the third application is to determine the roots of perfect squares, cubes, and so on. Alright, so if we need to determine the roots of any integer, as long as it gives us another integer, then we can use the prime factorization. Even though you can do this with your calculator in GRE, it might not be necessary, but it's good if you know it how to use the prime factorization to find the roots of an integer. Okay, so let's get these two examples quickly. First one says the square root of 14,400. What is the square root of 14,400? All right, now to find the square root of 14,400, all we need to do is let's express the number in prime factorization, and you can recollect how we did it the other time. So we have 144 times 100, and we have 144 as 12 times 12 times 10 times 10. Okay, we have 12 to be 3 times 4, another 3 times 4, then times 2 times 5 times 2 times 5. So this gives us 3 times 2 raised to the power 2 times 3 times 2 raised to the power 2 times 2 times 5 times 2 times 5. So then we have square roots of, this will be 2 raised to the power 1 power 1. So we have total of 2 raised to the power 6 times 3 raised to the power 2 times 5 raised to the power 2. So we express the number in prime factorization. Now all we need to do next, when you have found the square root, it means you should divide the powers by 2. Square root means divide the powers by 2. If you are doing cube root, you divide the powers by 3. If you are doing fourth root, you divide the powers by 4. So here we are going to have 2 raised to the power 6 divided by 2 times 3 raised to the power 2 divided by 2 times 5 raised to the power 2 divided by 2. So which gives 2 raised to the power 3 times 3 raised to the power 1 times 5 raised to the power 1, and that gives us 8. That's 2 raised to the power 3 times 3 times 5, and that is 24 times 5, which is going to be 120. So that is the square root of 14,400 using prime factorization. So it's just something that's simple as that. I can easily do square roots without calculator using prime factorization. Okay, and note from here, if you don't want to do prime factorization, you can also still just do something like this. So separate these two, square root of 144 times square root of 100. All right, so square root of 144 is 12, square root of 100 is 10. 12 times 10, 120. So you still have your answer. All right, so but we just did that to see how you can use prime factorization method to find the roots of an integer. Okay, so let's see the second one that says, what is the cube root of 4096? What is the cube root of 4096? So we are looking at cube roots of 4096. So the same approach here, we first need to express our number in prime factorization. So you can, let me just use another method, that's the long division, to do this, so that we will not just be using only the breaking into factors alone. So we can go by doing this as well to express our number in prime factorization. So I can start with 2, and in 4 I have 2. So I can drop the 0 down. In 9, 2 in 9 I have 4, remainder 1, giving me 16 here. 2 in 16 is 8. Now that means I can still go with 2, which means I have 1, then I have 0, then in 4, 2, in 8 I have 4. And I can still go with 2, which means I have in 10, 5, in 2, 1, and in 4 I have 2. Can still go with 2, which gives me in 5 I have 2, remainder 1, giving me 11. So in 11 I have 5, remainder 1, giving me 12, and in 12 I have 6. So I can still go with 2, which gives me 1 in 2, then in 5 I have 2, remainder 1, 16, I have 8. I go with 2 again, so in 12 I have 6, in 8 I have 4, and I go with 2 again in 64, or you should know that now, that's 32. 2 again, I have 16. All right, let's continue here. Then I can have 2 again, which gives me 8. Then 2 again, in 8 I have 4. 2 again, I have 2, and 2 again, I have 1. Okay, so this means my 4096 is 2 raised to power 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 raised to power 12. Okay, now we are finding cube root of 4,996. So, and cube root, like I said, means you are dividing the power by 3. This is 2 raised to power 12 divided by 3, which gives me 2 raised to power 4. And 2 raised to power 4 is 16. So that means the cube root of 4096 is 16. So that is 16 times 16 times 16. We give you 4096. Okay, guys, so that's where we'll be ending the second class on number properties. We will definitely conclude the topic in the next class. So like I always say, try to go through this lecture again and practice the examples by yourself and get ready for the concluding part of this topic. So see you in the next class. Bye.